Okay, so I'll make a start. So thanks first to the organisers for inviting me to speak here today. Start with some kind of an apology of sorts, in the sense that the work that I'll present here is only tangentially related to the kinds of free boundary problems that you've seen in the talk so far, but I hope you'll find it interesting nonetheless. So the overall theme of the work which I'm going to present has the somewhat grandiose aim to try and derive a suite of mathematical models that describe biological tissue growth, which accommodate microscale or mesoscale effects in a more rigorous way than is sometimes done. So why would you want to do this? So as a very brief motivation, I'll not bang this drum too hard, but as a very brief motivation, if you want to write down a model to describe the behaviour of a collection of cells, then broadly speaking at least there are two approaches that you can take. You can think about the dynamics of individual cells in whichever way you choose, cellular or subcellular, or some kind of mesoscale, or you can write down a mean field type approximation posed typically in terms of PDEs, which describes the collective behaviour. Benefits of each of these approaches are somewhat obvious, and in the sense that I'm going to use the terminology, multiscale methods can be used to develop tissue scale PDE continuum descriptions which carry some of the benefits or some of the advantages of the discrete or microscale description. So on this theme I'm going to talk about two problems. So firstly, the generation of a mathematical model which couples explicitly growth and transport at the mesoscale to a macroscale description, and then on the sort of discrete to continuum aspect, some analyses of front propagation in cell signaling type systems. So to concentrate on the first of those, as I've already alluded to, you can argue, if you like, that there are three kind of scales. You've got your cell scale, which may be discrete, and there's an intermediate scale, which is perhaps more concerned with tissue microstructure, and then you've got your tissue scale. And I'm going to concentrate on the second half in the first part of this talk, aiming to create a macroscale model which explicitly couples growth, transport and structure at this sort of pore scale into a macroscale model. So I'm using the terminology pore scale, and I've got a picture here of a kind of a scaffold, because I'm going to frame all of this, all of these discussions in the context of tissue engineering applications, where typically a scaffold structure is seeded with some kind of cell type and encouraged to grow, the idea being to create a piece of tissue which is of some utility. The method that I'll use is kind of well studied in the fields of poroelasticity and porous flow, but the distinction between those works and this being that growth and transport are explicitly included in what I'll present. So as is often the way, you take a fairly complex problem and boil it down to the simplest description that one can, with the aim of sort of elucidating the method and demonstrating that it's possible. So with that in mind, I'm going to consider my tissue, or my scaffold saturated with fluid, which contains its cells, and I'm going to consider scaffold and cells and ECM and all that kind of stuff as one solid material. Saturated with a viscous fluid, and the viscous fluid contains a passive nutrient, and the growth of the cells in the scaffold will be represented by the evolution of the interface between these two phases. So I've got a solid, so this is like a pore, and the interface between the two things moves, and that is my representation of growth, and that will be constitutively chosen to be nutrient limited. So this is a kind of moving boundary formulation at the pore scale. So to jump to the detail, because I'm assuming that things are solid and that the growth dynamics are represented by a moving interface, I can write down without much difficulty the sensible kind of equations which are valid in the fluid domain. So I've got flow equations and nutrient transport equations which are valid in the domain omega f, which is my fluid domain, and then in the solid domain not much happens because it's solid. What happens is I want to prescribe in some sensible way how this interface is moving to accommodate growth. So I write down mass balance equations which are valid on this interface, and these describe how nutrient is uptaken according to some rate q and how this uptake is related to the resultant growth that you get, which is some other function s, which is sensibly or reasonably stated to be dependent upon the amount of nutrient that you consume. The interfacial, or the growth itself is really represented by this interfacial velocity v sub fs, which appears in this mass balance statement. I can pick Q and S however I like, but doing the standard thing, I'll pick something simple but reasonable, and say that the amount of nutrient that one consumes on this interface is proportional to how much nutrient there is, and the amount of growth that is resultant is directly proportional to how much you consume. So in this sense, the free parameters R and alpha are a kind of uptake rate, and then a kind of efficiency, which says if you uptake a certain amount of nutrient, how much do you then grow? You can manipulate these equations somewhat to obtain explicitly what how the normal velocity of this interface depends on the constitutive choice that you make for your growth function, and how the resulting fluid flow is affected. So this is kind of a sort of moving Stefan problem type formulation, and in this simplistic representation, my moving boundary is like a sort of phase annihilation creation front. So as the solid grows, it's gobbling up fluid as it goes, and the velocity of the things of the fluid is going to be dependent on the density of the material that one creates as you move. So self-evidently, this sort of singular interface or non-material interface is a fairly simplified representation of what's really going on, because what's really going on is there's a finite thickness layer of cells living on this pore surface, and they're growing, and that's really what you're seeing. So if you write down something more sensible or more realistic in this finite thickness layer, what you can show is that this interface, this non-material interface limit, is just the limit in which the consumption in this layer outweighs nutrient diffusion by a very large amount. So it's rigorous if simple. Okay, so to crack on through this is the model that I end up with. I've got my flow equations and then some growth boundary conditions which describe what's going on, and I've specified Q and S, my uptake and growth functions, to be this simple form, but I could of course have chosen anything else I like. An important feature here, which I'll refer back to, is my non-dimensionalization of time. I'm looking at a time scale of advective transport at the macro scale through my scaffold, and this will become important later. So this is my microscale model valid in this little pore, and I want to upscale that to my tissue scale. And the way one does this is to say, well, the pore is significantly smaller than the tissue. You've got well-separated spatial scales between these two things, so you can asymptotically expand everything. And if you do that, then you expand in your multiple scales form, and you obtain a bunch of equations at each order which describe the dynamics. I'm going to make one further simplifying assumption which simplifies my leading order problem, and that is that the growth and transport dynamics are next order, so they're small compared to the time scale of flow, and this is not an unreasonable statement, even if it is a simplification, in the sense that within these kind of tissue engineering structures, on the time scale of flow, cell proliferation and ECM deposition is likely to be a small thing. So even though it is chosen sort of for mathematical convenience, it's not unreasonable to do so, I claim. If you believe all of that, then you end up with this leading order problem, which is quasi-static. So I've got a quasi-static domain omega. The omega is currently completely general. I haven't specified it yet. And then at next order, I bring in my growth and uptake terms which drive variations in pressure and flow and so forth. This being something of a classical problem, you can bring to bear all the classical sort of approaches, and what you find is that the flow is determined by a macroscale pressure gradient mediated by a microscale permeability, which I've denoted here K, and that permeability solves a Stokes flow problem in the microstructural domain. So the shape of omega and this Stokes flow problem determines how the microscale permeability influences the flow. So I can solve for the flow if I like. I don't particularly like, but I can. But I can't solve for the nutrient concentration, as it's undetermined at all orders. But that doesn't really matter, because I don't really mind, or I'm not really interested in doing complicated simulations of the microscale flow. I'm interested in deriving a macroscale model. So I can crack on and do that essentially by integrating out all of the microscale dependence. So I integrate over my domain, and I apply the boundary conditions, and I apply this sort of hidden boundary condition, which is that locally all of these pores look the same. So I've got periodicity on my pore structure, but on the macro scale I can have different shaped pores, but locally they must look the same. And this is the crux of the method, really. That's the scale separation. And if I were to do that, so you integrate, you apply boundary conditions, you use the divergence theorem until you wish you didn't, and you obtain a bunch of equations which are valid at the macro scale. So this is the sort of the final slide, really, of this part, which shows you the model that you obtain. So there's some hidden detail, but this is what you get. The important thing to point out is that these integral averages are the key to the thing. So this is what carry in a sort of rigorous way the microscale information up through the scale. So you lose some information because you're integrating it, but you do carry rigorously that information up in a way which I'll explain. So what does the model look like? Well, it looks like Darcy flow, which is nice because it's something that everyone understands. It looks like Darcy flow mediated explicitly by the microstructural information carried from the solution of a Stokes flow problem. But moreover, and this is where this model differs somewhat to others, moreover the pressure which you obtain, the pressure in the fluid, is influenced explicitly by the form of the growth that you choose through an average. The transport that you get that goes along with this is similarly influenced by the advective flow, and then explicitly by growth and uptake in the reactive terms of this equation. So that's my model posed completely generally. I can plug in the constitutive laws that I've chosen for the sake of this discussion, and I've now got a system for V, P, and C which I can solve at the macro scale given some appropriate initial and boundary data. Which is something that I will do because having done all of this analysis to get this model, the obvious question to my mind is how important is all of this? You've ended up with Darcy flow, and we all know about Darcy flow, so why didn't you just write it down in the first place? So a simple way to examine whether or not this is of some kind of import is to just solve the thing for some geometry omega and show that it does indeed matter. So this is what I'll do. I'll take some somewhat arbitrary experimental data from a collaborator and use that to define my computational domain omega. So I've chosen a 2D slice through a tissue engineering scaffold, and I've picked a lump, and I've said this is my growing piece of scaffold with cells living on its surface, and it's growing away, and I'm going to solve the problem and see what the flow and nutrient distributions look like. And if I do that, then I can obtain my average permeability tensor valid at the macro scale for this geometry. I can compare that to something much simpler like circles, something nice and isotropic, and you can see essentially that these matrices are different. That's the point. So the microstructure matters quite significantly in how the macro scale permeability is calculated. But how does that affect the nutrient transport through the scaffold is the real question, because in my model at least, nutrient availability is analogous to cell growth. So I picked S was equal to C, broadly speaking. So if I were to study a problem of import in tissue engineering, which is the point of using these kind of bioreactor systems which I have in mind, is that you want to get nutrient to all the cells in the scaffold. So that's why you would perfuse them with nutrient that carries, perfuse them with culture medium that carries nutrient. So just to see what happens in my, yes?
Relate that blue dotted circle or sphere with the two square pictures.
Yeah, okay, so what I've done is this is a 3D picture, or sort of a picture of a scaffold. It's about the size of your end of your thumb. It's like a little hard sponge, and I've taken a 2D slice through it, and then at random really I've just picked a small piece of this, and I've said that this little lump is now my little grain of scaffold in 2D. So obviously this is a 3D interconnected structure, but in 2D you have a little lump of scaffold, and this defines my periodic geometry omega. So then I can solve my Stokes flow problem in this geometry using COMSOL or any other technique you like, and that gives me my permeability tensor at the macro scale.
So you calculate on it, so that matrix AF is determined by solving Stokes flow in this.
Yes, that's correct.
That's in that picture on the left. And one on the right is if you solve Stokes flow for that geometry, then you get this KF.
Yes, that's right. Yeah. Okay. So sorry, I didn't explain that clearly enough. So if you do that, you carry through this information. So this is how you carry the microstructure forward up into the macroscale problem. So this tells you how the structure affects the flow, but you still haven't decided how the growth affects the flow or the uptake affects the flow, and you want to do that, or the transport rather, do that by solving the PDEs that I showed on the last slide. So I'll just skim back.
Sorry, okay.
Yeah, of course.
But if you were to do this to the whole of that domain,
Yeah.
with the slides, you get different KFs everywhere, wouldn't you?
Yeah. So this geometry here really is just picked at random to show that the geometry that you choose matters. So the method itself is predicated on the fact that your tissue or your material microstructure is locally periodic. If you apply it to something that isn't locally periodic, then you have to take the results that you get with a fairly large pinch of salt, because you're not really representing the macroscale tissue. But what this is intended to show is not that this thing is a well representative selection of this whole picture, but that if you were to choose something, then you do get something different. So it's a somewhat trivial statement, but it seems to me to be worth making. So what I'm thinking about now is this scenario in which I put some nutrient in the top of my scaffold and I allow the flow to perfuse it through, and I want to see where it gets to, under the assumption that I have this structure or this structure, and I have some growth going on. And if I do that, then I can get the following results. So this is, I'm looking down through the scaffold, I'm flowing down, carrying nutrient from the top somewhere towards the bottom, and then these graphs are vertical slices. So the main important graph is this one here, which is how the nutrient is transported through. So as you evolve your simulations, the nutrient concentration and all the other variables evolve to some kind of steady state distribution governed by the uptake and growth parameters.
Should I think of that as a periodic, those little blue things as periodic?
Yes.
Okay, and
But this,
each of them has the same KF, and although that object doesn't look periodic, that's what
yes,
going
yeah,
on.
that's just a sort of a picture to frame the discussion, really, rather than, I'm not claiming that this, for the specific material at hand, this is not necessarily a good representation, but for materials of relevant kind, this would be. Does that make sense? Okay. So what you obtain, if you have a nice isotropic periodic material, you get this nutrient distribution. Nutrient starts up here and it gets right down to the bottom of the scaffold or material, and one would infer cell growth throughout. Whereas if you have this more complicated microstructure, then nutrient is being consumed at such a rate up here that it can't really get through to the bottom. So you're going to have cells or something else at the bottom of this scaffold which are starved. So what is my conclusion from this? Well, the conclusion really is somewhat trite, which is that the microscale matters. Sorry, the microstructure matters and the microscale dynamics matter, which is perhaps a non-statement, but the way in which I interpret that is that if you're going to write down the kinds of macroscale models which people want to do, then you have to really think about how much you care about the microstructure. If you think the microstructure, or how much you know about the microstructure, because it has a very, very significant influence on the solutions that one obtains. So if you were to write down Darcy with a nice constant permeability, you might get this straight line and think, well, whoopee-doo, that's my concentration. But in fact, if that constant permeability does not well represent your structure, then this is really what you should expect, and your model is really not representative of what you see. Okay. So that's the first part of the talk. I'm now going to move on to something somewhat different, which relates to the sort of left-hand side of the picture I showed right at the beginning, the cell description to the continuum description, rather than the microstructure description to the macroscale description. So as a model problem for this, and a common one in biological applications, cell signaling type models are often posed as discrete coupled sets of differential equations, so spatially discrete diffusion type problems as the model problem I'm going to look at. And a phenomenon of interest in such a system is the propagation of boundaries of activation. So you've got some cells that are signaling to each other and they're propagating this information forward, and that has implications for things like cell differentiation and the like, the details of which I'll skip over because I'm going to look at these more mainly in a very idealized framework, but the conclusions carry. Some things which are of importance in these systems, if you're thinking about propagation, is how does the underlying lattice, or how does the coupling between cells influence how the thing propagates, and at what speed is this thing propagating. So if you want to estimate the speed of propagation, how do you do it, and how do you know whether or not your estimate is going to be accurate? And broadly, there are two different estimates that one would make. The estimate that the leading edge dynamics form a good description of the front speed, or that they don't, and you have the whole nonlinear front which determines the propagation speed. So to look at the first of these, and to consider this sort of toy model problem, I'm considering a spatially discrete diffusion equation with a monostable nonlinearity, and I'm looking at waves connecting the stable state to the unstable state in a monotonic fashion. The standard thing to do is to write down a travelling wave ansatz and this is the discrete analogue of the normal travelling wave ansatz, and you obtain a differential difference system for the wave speed, which is of the size of your lattice. So it's not a trivial problem. Instead of doing this, what you can do is write down a WKB type ansatz for your solution, where t is playing the part of your large parameter, and obtain, instead of a differential difference system, this set of equations here, which are algebraic equations for phi parameterized by various gradients. The point really here is that the lattice structure, so here I've got one for squares, the lattice structure is embedded in these Koch terms, and the analysis carries through in exactly the same way if you were to pick, skip through there, if you were to pick some other geometry. As long as it's regular, the analysis works nicely, and you end up with this nice simple representation. So what's the use of this simple representation? Well, I'm thinking of linearly selected or pooled waves at the moment, and so the wavefront is given by the points in phi eta space at which phi is equal to 0. So that's the point at which the linear approximation breaks down. So that defines where your front is. And if you can solve the equations for the point phi is 0, which you can because they're not particularly complex, then you obtain the wavefront. So does it work, is the obvious question. What you find if you were to simulate the nonlinear problem in a discrete lattice is you find that you have a maxima, or you have maxima in wave speed on the on-lattice directions and minima in the off-lattice directions. So in squares you'd have maxima as theta is 0, theta is pi over 2. In hexagons you have more of them, and pick any other geometry you like that tiles the plane, you'd have more maxima and more minima. And these are reflected in the solutions that you get. So these are numerical solutions for the speed against theta, showing maxima at 0 and the end, and a minima in between. And this is the results you get from the WKB equation, which reflect this. So this is the relative speed between the fastest and the slowest point, showing that you get two maxima and one minima, or if you're in hexagons, you have more of them. So not only is it relatively easy to construct this, but because the form of the equations is quite nice and simple, you can do some asymptotics and reconstruct explicitly what the shape of the wavefront is in the limit that the coupling between lattice points is very weak. And if you do that, you can reconstruct the wavefront. You can compare numerically how these limit cases, so that the relative speed between the fastest and slowest, how they compare with the numerical simulations for different coupling strengths. And you see that they converge down to that. So the asymptotics and the approach compare favorably with the nonlinear numerics. As I stated at the beginning, this is all in a very idealized model. I picked a spatially discrete diffusion equation as its classical, but that bears very little relation to the kind of complicated cell signaling models that you might want to write down. But you can do it just as well in any complex cell signaling model you care to throw a stick at. So taking a fairly simple one, the classical delta notch signaling model, which displays period 2 patterning behavior and invasion, you can do exactly the same analysis. You just end up with a slightly more complicated equation for phi, but it's only quadratic in phi. And you can work out the wave speed, and this is a plot of wave speed versus some parameter, and you see that the dots and the lines match up. A point which is worth making is that in these cell signaling models, these waves are not necessarily monotonic, which is what I was analysing in the first part, but the method just coped with that nice and easily. There's no real more difficulty in tracking this modulated travelling wave than there is in tracking a monotonic travelling wave. Okay, so to wrap up, just one more thing. So this is somewhat hot off the press, so I'll skip over the detail. But as well as lattice dependence, the other thing you might care about is how fast this thing's going, or how good your estimate of how fast this thing is going is. So take a very similar equation to the one I've analysed previously, with a slightly different nonlinearity, the reason for this one being sort of historic, and it allows you to move around parameter space to move from a pulled to a pushed regime. The continuum analogue to this has been well studied historically, so sort of 70s was when many of the results were done for that, and it's well characterized. You know the speeds in each regime, and you know where the transition between the different regimes are. But in the discrete case, it's not quite so simple. So in the discrete case, pooled fronts are relatively easy to construct, and you can obtain equations, sort of a dispersion relation and repeated root condition, which tells you what the speed is for any given parameter set that you care to choose. But in the case of pushed fronts, it doesn't work quite so neatly, and you require some asymptotic results in the limit of weak coupling. And these are they, so I'm just, as I say, I'm going to skip past these, but just suffice to say these estimates exist, and some numerical simulations are currently ongoing showing that within certain regimes of parameter space they form a good approximation. As one final remark, if I choose a slightly contrived nonlinear coupling term in place of the standard constant coupling term between lattice points, one can in fact construct all of the waves explicitly that you want to. So stable to unstable connections, you can construct both pulled and pushed, and stable to stable connections, you can construct wave speed estimates explicitly. But it's in somewhat of a contrived form. So to summarize, I've tried to describe a bunch of work which comes from the approach of trying to represent microscale phenomenon of relevance to biological systems in a macroscale description, and to show in what regimes these things are likely to be important, and in which regimes you need to account for them. So to do so, I've shown that via a sort of microscale moving boundary formulation for growth, that microstructure and growth is an important aspect of the macroscale dynamics that you observe in solutions. And secondly, that a slightly different way of analysing front propagation in systems of relevance to cell signalling descriptions provides a nice, powerful way of analysing wave progression. I'll finish by just thanking the people who were also involved in this work. So the first half of this talk was funded by a research fellowship in Occam with Helen Byrne and Sarah Waters. Martin Nelson at Nottingham Trent did the numerics, and Alicia gave me the experimental data, which I somewhat misused on these slides. The results for pushed waves were done in conjunction with John King, and I'd ask you to direct your questions to him on that regard. And here are some papers which contain the results. Thank you very much.
Thank you very much. There's time for a couple of questions. What are the non-theoretical results about this? I mean, existence and so on. These are known?
I'm sorry?
Theoretical results about the existence of solution and so on. Is it theoretical study?
It's not something that I've studied, so I'm not able to answer that question.
So I have a question concerning this periodicity again. You assume that, well, you first convinced us that the local structure, microstructure is important for the macroscopic behavior, but then you assumed that a certain type of microstructure of microscale geometry is periodic. It was not the case in any of your pictures. So maybe it's not the case in reality sometimes. The question is, you solve one cell problem, 4, because it's periodic. Is it possible to extend your approach to many cell problems for different regions of the macroscale geometry. So some sort of numerical upscaling which is done sometimes.
Yes, I guess there's sort of two comments there. Firstly, the choice of pictures is perhaps unwise because it highlights the flaw in the work, but I like to be honest in there. But equally, in terms of the variation of these periodic units, so I've taken the simplest possible case where the permeability tensor that you get is just a constant, so that reflects it being equally permeable in this sense everywhere in the domain because it's periodic. But you can have macroscale variation in that permeability tensor K, for example, so you can prescribe some macroscale variation. So in that way you could do it smoothly, analytically, but you could equally have different regions in which you know something about the different periodic units and then you'd have a matching layer between. So I guess in short, yes, that's the answer.
Okay, thank you.
So, thank you again for